Thank you. Yeah, of course, I would like to thank the organizers for organizing this wonderful celebration. So as my student noticed, it feels like a big family meeting. So I'm honored and happy to be part of this big family. And yeah, I will take the opportunity to say a few words about a project that it's slowly but surely advancing. The first paper appeared 2 months ago, and it's a work in progress. So while preparing these slides, I was looking for some pictures with Philippe and me, but I didn't find any, and I asked Google if it could find some pictures with me and Philippe, and well, that's the result. In fact, we wanted with Patrick, we tried to have some pictures of you in Les Houches, maybe not shirtless like the one with Jean-Bernard and Hubert, but yeah, somehow that was the year when both the lab and Philippe had an existential crisis. So Jean-Bernard showed a picture of you trying to save the IPHT, and then you needed to be saved. Yeah, so in fact, you took a trip to Tokyo a few months after, and I don't know, you came back full of energy. So you have to tell me what happened in Tokyo, because I want to find your secret.
You have to ask Jimbo.
Okay, I will try to find him in Tokyo this summer. Yeah, so that's 6 months later after this trip. You have this this picture at the conference Integrability, Engagement, String Theory that we organized with Fedor and Ivan and other people. So Philippe and Renata are here smiling and happy. And then the second picture that Google found with both of us is from the celebration in last November, 60 years of IPHT. So I start to see some correlation between your life and the life of IPHT, and I start to believe that the PH here is from Philippe. So yeah, so okay, so that's how it goes for the life, and then so let me say a few words about. So yeah, I didn't have the opportunity to collaborate with Philippe, but I worked with his first student, Frédéric Lesage, on some on the model that, in fact, the model that Kolya presented before the lunch break. This big family of Calogero-Sutherland, Calogero-Moser models. So in fact, secretly, the work I'm going to talk about is also from this family. In fact, Kolya talked about the Haldane-Shastri spin chain, which comes from a bigger family of dynamical models of Calogero-Sutherland type. He talked about the isotropic model, where the spin interaction is isotropic. And here I will mention work where the Haldane-Shastri model is Q-deformed. The spin interaction is anisotropic. And in fact, we are going to look at a particular point, Q equal I, of this Q deformation. And this can also be seen as a long-range deformation of the XX model. So since it's XX model, it's free fermions, and there is a nice formulation in terms of temporary leap. So I already talked about this model at previous conferences. I talked about it in the language of the spin chain. Today I will use the language of free fermions because that's the particular point that is we are interested in. So I will mostly forget about Haldane-Shastri formulation, spin chain formulation. One of the features of this model is that it doesn't have obviously translational invariance, but there is something which replaces translational invariance. So it will be very important to solve the model to find a nice formulation of the model. So this remark is also related to the conditions of periodicity conditions or boundary conditions. So the fact that we have this some particular boundary conditions on the circle, this condition renders the fermions non-unitary. So it's intrinsically non-unitary system. And well, we are also used to have different behavior for spin chains. We are used to have different properties of the odd and even length spin chain, but in this particular case, the difference between odd and even is even more radical. So today I will focus on the odd length spin chain. So, and I will leave the even case for later. So let me first introduce the ingredients. So it's a different language than the one that Kolya used. So I will use this. So I have a one-dimensional lattice with n sides. I have a kind of spin chain. And the degrees of freedom at each side are fermions with anti-commutation relations mentioned here. So you see that we have this -1 to the power I, this staggering here, which renders the fermions non-unitary. There is some mapping to the usual Jordan-Wigner fermions that we use to solve the short-range XX spin chain. So there are some square root of 1 in the definition of the fermions. So I pretend that this is the natural formulation where I introduce these i's, which render the model non-unitary. And the fact, so once I have this definition here, I can define some global symmetry algebra, well, some global generators. In this case, I can define some generators of the GL11 algebra by the usual definition. So the raising of the annihilation operators are lowering operators, the creation operators are raising operators, and then the magnetic-like number is given by this staggered number of fermions at each side. And well, here there is a central generator. Well, the value here is in fact specific to the odd length spin chain. If it was even, this central charge would be 0, and there would be consequences of this, the fact that the central charge is given to 0, so by 0. So we have these global generators, and then I can change coordinates from the fermionic degrees of freedom at each side. And pass to the linearly independent generators, which are given by these F1s, and fermions which are defined on 2 nearby sides. And if you are trying to compare, I mean, to see what algebra obey the 2 kind of objects, you see that these 2 side operators commute or anti-commute with the generators of GL11. So this will be important for the construction of my Hamiltonian. So once I have these fermions, I can build the temporary Lie algebra, which will be just this combination of the two side operators. And they obey the usual relations of temporary lib, where the particular you see that we have specified here the value of the parameter. So usually you have here q plus q minus 1, so q plus q minus 1 when q is equal I will be 0. So that is what I call free fermion temporary Lie algebra, a particular point in the particular example of temporary Lie algebra. So as I mentioned previously, that these operators G commute with with GL11, the global GL11, but they are not the only ones. I mean, GL11 are not the only ones which are commuting with temporary lib. Also, these quadratic combinations in the fermions are also commuting with temporary lib. This representation, in fact, can be found in a paper from 13 years ago by Hubert and his collaborators. And in fact, this generator here, GL11, and these generators come from the degeneration of UQ of SL2 at the point Q equals I, which is supposed to be which is the commutant of the temporary Lib algebra. So now I'm going to define finally my my model, my Hamiltonian. So first I will the object that I'm looking at are defined naturally in terms of nested commutators of temporary Lib generators. So nested commutators means that you take a commutator, you take the commutator with the next the E at the next site, and so on. You can use the you can use the identities between the different nested commutators to see, I mean, to simplify the commutation relation. So the Hamiltonians I'm going to look at. So there are I have an integrable model with a series of conserved commuting charges. So the first one is chiral in the sense that, in the sense that I will explain later. So the interaction between sites is given by this nested commutator between sites I and J. So here I have to have all the temporary Libs from between I and J. Otherwise, this nested commutator is 0. And they are combined with some weights which are explicitly known, but they are a little bit complicated, so I'm not going to give them explicitly, but yeah, we know them. And we have two different chiralities of the Hamiltonian, so there is some parity transformation between these coefficients, and it happens that in fact they are the opposite to each other. So h left is minus h right. So in fact, just one of them is linearly independent. And then there is another Hamiltonian which is non-chiral in the sense that if you parity transform it, you will get the same object. And this is written in terms of anti-commutators of nested commutators with some, again, sum over all the sides of the chain. And if you are looking here, you see that there is no interaction on the other side of the of the chain. So the indices are just from 1 to n, and the interaction is not invariant by translation. So it looks really very complicated, but in fact we are looking at a complicated object which is in fact very simple. And the key to see that this simplicity is offered by this quasi-translation operator. So this generalizes the usual translation operator on a lattice, which would be a product of permutations. This quasi-translation operator is given by a combination of temporary Lie operators with some coefficients. I don't know if you see here, but tk is given by tangent of pi k over n. So all these coefficients here are written in terms of this tangent, and all these different Hamiltonians, these different operators commute among themselves. So this object generalizes the x6z Hamiltonian, which would be just the nearest neighbor interaction, and if delta is equal to 0, we have the EJs that I have that have the commutation relations that are given here. I mean the algebra that is given here. Yeah, so a small comment. I was saying that you have seen that I have an I in the definition of the this chiral Hamiltonian. This is done. I mean, with this convention, the spectra of both Hamiltonians is real, although they are not these Hamiltonians are non-unitary. And the reason seems to be the fact that we have some PT symmetry. So if we define the parity by changing the reversing the sides, and time reversal symmetry by just an antilinear operator that leaves invariant the temporary leaves, the action on the different conserved quantities given by is listed here, and we see that PT leaves all the Hamiltonians invariants. There is a bonus symmetry which is charge conjugation that I'm not using here, but yeah, so that's these are the discrete symmetries. Now the spectrum of this object, the Hamiltonian, looks very complicated, but in fact the spectrum is very simple, and the spectrum is given in terms of a collection of numbers which are called the motifs, which were defined for the Haldane-Shastri model. So this we have a collection of m numbers, integers, which are between 0 or 1 and n minus 1, in fact. So this these integers obey the following exclusion rule. Mu, the difference between two successive n's, mu's, is bigger than 1. So if I represent them by these occupation numbers, in fact, two black dots cannot be close to each other. So that's what we have seen in the isotropic Haldane-Shastri model, and this is also valid in this case. So in the terms of these motifs, the spectrum of the quasi-momentum is given by the sum of these numbers modulo m divided by 2, multiplied by 2 pi over n. The chiral Hamiltonian has a chiral dispersion relation, so that this is why we call it chiral, and it is staggered. There are, you see that the dispersion relation is different if n is even or odd. And the non-chiral Hamiltonian has a dispersion relation which is also perfectly linear and non-staggered. So maybe you are going to ask me how do we know that this is true? So it is true because we know we have this construction of the Q-deform Haldane-Shastri model, which explains the spectrum and the degeneracies. We also know the wave functions in terms of particular McDonald polynomials. And there is a whole history of this Q-deform Haldane-Shastri with origins in a paper by Denis, Vincent, Michel Godin, and Duncan Haldane, using Daha, the double Heineke algebra. This deformation was almost forgotten for many years, except for some very nice works of Uglov in the 90s, and then Jules simplified this model, and we wrote a paper with him and Vincent Pasquier writing down the structure of the wave functions and so on. So the limit Q equals I of this model will give this all these properties of the spectrum and so on. So yes.
Just to let you know, if you want to save time for questions,
yes.
Then you have about 5 minutes.
Yeah, I will. Yeah.
Closer to 10.
Yeah. Okay. I will go a little bit faster. So the key to find a nice formulation of this model is to use the fermions on the first side of the chain, and then transport it with this quasi-translation operator. In fact, I have to thank Jean-Bernard for asking me the previous conference what is this quasi-translation operator. So while trying to explain him what is the role of quasi-translation, this is how we found this nice formulation of the problem. So we transport the fermions with the quasi-translations. This transformation is periodic because g to the n is equal to 1. So it's almost like for the usual fermionic operators, but now the anti-commutation relations of this object is non-local. So the pluses and non-pluses are anti-commuting to 0. And the ones which are non-trivial, you see that they anti-commute to some number which is not 0 for any pair of sides. But the nice property is that this was this tangent of pi j minus I over n. So the anti-commutation relation is translationally invariant. So now we can use Fourier transform, Fourier representation to write some Fourier modes. So we transform these phi operators, write their modes, and in fact we have to rescale with some. We want to rescale the definition of the Fourier modes with some numbers which are given here, such that we get canonical anti-commutation relations for the Fourier modes. So once we got these canonical anti-commutation relations, we are ready to do many things with it. So in particular, the 0 modes are the generators of the GL11 algebra that I have shown you earlier. And the other modes, the non-zero modes, in fact, they are linear combinations of these two side operators that are commuting, in fact, with the GL11 algebra. So this ensures that yeah, that the non-zero mode commutes with the zero modes. So we are almost there. So now if I want to rewrite my conserved charges in terms of these Fourier modes, it's very easy to see that the chiral Hamiltonian is quadratic in the fermions. So it's the Hamiltonian is just a free Hamiltonian with some numbers here, which are in fact the energies of these occupied states in the motifs, and this Hamiltonian can be diagonalized on the Fourier Fock space, which is spanned by the modes, by the Fourier modes of our fermions, with numbers from 0 to n. So this looks very much like the spectrum that we have cited here, except that here the Fourier modes, the occupation modes have these restrictions, these motif restrictions, while here they are just purely fermionic occupation numbers, so the n's can be separated by 1 unit. So it's a bit, it can seem a little bit contradictory, but in fact the two representations are compatible due to some degeneracies in the spectrum, which are related to this equality between these two staggered branches of the dispersion relation. So this Hamiltonian is consistent with the motif rule. And then if we are looking at the next Hamiltonian, it is quartic in the fermions. There is a quadratic part and there is a quartic part. So the quadratic part again has the dispersion relation encoded into it. And then there is some interaction between the fermions, which ensures, in fact, this part here ensures the statistical repulsion, and so it ensures that we have this rule here when we are computing the total spectrum of the of our Hamiltonian. So experimentally, by numerical experiments, we have obtained that this interaction, this potential for fermion potential has this particular value here, which is compatible with with what we know about the spectrum.
So you have hard limit of 3 minutes.
Yeah, I'm almost there. Okay, so we succeeded to have a very simple representation of our model in terms of fermions. For odd length. For even length, the spectrum is very strange. It's identically 0. There are a lot of Jordan blocks. So that's something that we want to do next. So you have seen that there is a lot of symmetry in addition to the global GL11 symmetry. So we know that for generic Q, this is the quantum affine GL2. We think that at Q is equal Y, this algebra will degenerate to GL11 Yangian, but that's something that we have to prove. We have to understand the staggering in the dispersion relation that appears in the odd case, and yeah, an important problem is to see what is the CFT limit when we take large size limit and we are looking at the excitations around the antiferromagnetic vacuum, equivalent of antiferromagnetic vacuum, we'll see some. We think we'll see some conformal field theory appearing, and with an extended symmetry, because we have the extended symmetry in the a finite size case. So probably this will become the GL11 Kac-Moody algebra level 1. That's the natural guess, but of course we have to check it. So if this is true, there should be some free field realization and some vertex operator algebra that probably will also help us to understand the relationship with the wave functions and the McDonald polynomials that I have mentioned previously. And there are other roots of unity that will give other a super spin chain formulation of the model. So that's also something that would be very interesting to look. And the point that I wanted to add, and I forgot yesterday evening after all these food and drinks. In fact, Jules and his collaborator Rob Klubbers managed to obtain anisotropic deformation of the Inozemtsev model, which interpolates between the short-range model and the long-range model. So it's a kind of elliptic generalization of this model. And of course, there is a q equals I point there, and we would like to also to understand what happens with this model, which interpolates between short range and long range. And yeah, so that's what almost all what I wanted to say. So by the end of preparation of my seminar, I got pictures of Philippe and me in the garden of joy and research at IPhT. So happy birthday, Philippe, and long many years surrounded by friends and by roses, and a lot of productive years in front of you, I hope. Thank you.